Hello. Today we're going to look at two more tests that are going to help us determine the convergence or divergence of some of these infinite series we've been looking at. And they are the ratio and the root tests. The ratio one is probably the most commonly used, but we will see both. But let's start straight away with the theorem for the ratio test. Okay, so a and again are going to be a sequence, and those are the terms of our series, our sum. And we're going to take this ratio here. We're going to take the ratio of the n plus 1th term over the nth term. We'll take the absolute value of that, just in case it's an alternating series. Okay, we can just use that. And we're going to take the limit of that ratio as n goes to infinity, and assuming we can find that limit, we're going to call it L. And this L is going to lead us to one of three conclusions. If that L is less than 1, then we can say that the series converges, and that includes 0. 0 is a possibility there. If the L is greater than 1, and that includes infinity, then we can say that the series diverges. However, and a little frustratingly, if the L equals 1, the ratio test essentially hasn't told us anything. It's not told us it diverges or converges. It might do either. The test is inconclusive. Okay, and that can happen sometimes. So we'll start with an example. Okay, we have a sum, we have an n to the 4 in the numerator here and an n factorial in the denominator, and it's not clear just by looking at it what that's going to do. So we'll take that ratio just as we said. So we take the n plus 1th term over the nth term, and pretty much always with these ratio tests we get a fraction over a fraction here, which is a little ugly as it is, but it gets a little easier if we take the reciprocal and multiply like this. And as you do these, you might get a little quicker. You might not have to put every step in here as we're doing, but for our first example, we'll certainly do this. And actually, we'll do one more simplification step. So we have the factorial terms sort of here and here, and we have the power of 4 terms here and here. So it's just a little algebra step to put them next to each other. Okay, so we have the n plus 1 to the 4 over n to the 4. We have the n factorial over n plus 1 factorial. Now we can simplify this. Okay, since both terms here are to the power 4, we can just combine them. And this n factorial over n plus 1 factorial simplifies like this. If you're not sure about that, let me just take a quick example. So we take 4 factorial over 5 factorial. Hopefully you can see when you write it out, all the terms cancel apart from the 5. And that's exactly the same that's happening here with the n factorial and the n plus 1 factorial. Okay, so we have this n plus 1 over n to the 4 multiplied by 1 over n plus 1. Hopefully you can see this term is going to go to 1 as n goes to infinity, whereas this term is going to go to 0. So overall, if we have 1 times by 0, this limit is 0. And if you remember our formula, our theorem, it said that if L was less than 1, then the series was convergent. So we can make that assumption now that this series is in fact convergent because this ratio test has given us L less than 1. So we take another example. We have the sum to infinity of 2 to the n divided by n to the 5. Again, we'll just take this ratio, the n plus 1th term over the nth term. You'll notice in the previous example and this example, I'm just kind of dropping the absolute value terms because all the terms are positive, so I don't worry about that. And again, we get this fraction over a fraction, but we can simplify that a little bit by taking the reciprocal of the denominator. And I've leapt to this point where we have the similar terms on top of each other here. It just helps us a little bit with the simplification. And hopefully the simplification here is fairly straightforward. We have 2 to the n plus 1 over 2 to the n. Well, sort of cancel the 2 to the n, and we're just left with a 2 in the numerator. And here, because both terms are to the power 5, we can just combine them. And so we're left with the 2. And then we have this whole fraction all to the power 5. Again, hopefully you can see that what's inside here is going to go to 1 as n goes to infinity. So we're going to get 2 times by 1, which is of course just 2. And this time our conclusion says that because 2 is greater than 1, this limit we got is greater than 1, this series is divergent. So our conclusion in the previous example, when L was less than 1, was that it was convergent, and now it's divergent. Okay, one more example, and I'm going to let you try this, so I suggest you pause the video about now and try to do this yourself. Okay, So here is the algebra, and I've gone through it pretty quickly, but in fact, rather frustratingly, it turns out that using the ratio test we get 1 here. And remember that 1 told us that this was inconclusive. Essentially, it didn't tell us anything. That's annoying. So even though the ratio test didn't actually tell us anything here, we can use another test. We've previously seen the comparison test. And if you take the comparison test and compare this with 1 over n to the 5 over 2, so take the n to the power 5 halves, you will find that in fact this series converges. However, we didn't find it with the ratio test. Okay, so this looks pretty similar. The root test has a similar kind of setup to the ratio test, except this time rather than taking the ratio of the n plus 1 from the nth term, we're actually just going to take the limit as the terms go to infinity, but taken to the power of 1 over n. And because of this 1 over n, we generally only use this if we have something to a power n in our series. We'll see an example of that in a second. Otherwise, it just tends to not work, or it tends to be kind of difficult. But with this limit approaching L, we still get the same kind of conclusions. If L is less than 1, then the series converges. If L is greater than 1 or infinite, then the series diverges, and if L equals 1, then the root test doesn't tell us anything. So hopefully this looks kind of familiar. It is very similar to the ratio test. If we take a quick example of this, and as I say, we do have something to a power n here, so that's a clue that we might use the root test. We'll dive straight in, and we'll take the limit as n goes to infinity of the terms to the power 1 over m. So just plug the term in here, n to the 4 natural log of n to the m. Again, we have to simplify. On the numerator, we'd have n to the 4 to the 1 over n, which we can just switch the order of the exponents to make it n to the 1 over n to the 4. But in the denominator, we've got n and a 1 over n, and so they just kind of cancel. So I say, in the numerator here, we have n to the 1 over n to the 4. Denominator, the n and the 1 over n are just kind of cancelled out, and we're just left with the natural log of m. It's still a slightly difficult limit, but you can use L'Hopital's rule and take natural logs in the numerator there, and in fact the numerator goes to 1, whereas the denominator is slowly going off to infinity, so we have 1 over infinity. In fact, this is going to 0. The limit of this is 0 as n goes to infinity. And again, our conclusion from this is therefore that this is convergent. That's what we conclude if L is less than 1. Okay, so that's about it for the ratio and the root tests. I'd say they look pretty similar, and applying them is relatively straightforward. I suggest you try a few examples and see how you get on.